thank you very much, organizers, Simeon, Anton, and Paul, for inviting me here. Beautiful place, wonderful conference. So I'm going to talk about the conventional Euler fluid, but I will try to explain how to couple it to axial gauge field. And the work is done with collaboration with Paul Wigman. There is some work in progress with Andrea Capelli, but I will not talk about that yet. Okay, so that's the outline. So I will introduce, first of all, one-dimensional analog of the story I'm going to talk about, very oversimplified, and then I will talk about barotropic fluid and how to do variational principle for hydraulic fluid dynamics, and finally how to couple axial gauge field and some manifestations of that coupling. So the quantum anomalies play an important role in quantum field theory with Dirac fermions, and sometimes these Dirac fermions can behave as fluids. So there is a question, what are the effects of the anomalies on the fluid dynamics of that fluid? And the early work, it was pioneered by these people, and I'm pleased to say that some of them are present here, even as a chair of this session. So basically what I'm going to say is that hydrodynamics, which is essentially Poissionization, it captures anomalies in one dimension, like fully, and the question is, what are anomalies in conventional three-dimensional Euler fluids? Can we make some analogies with that? The technically approach will be based on so-called geometric fluid dynamics approach and variational principles, and it's close to the ones of Lichnerovich, Carter, and then Arnold's school, as well as Marsden, Holm, etc. There are many works on this. And as a connection to this particular workshops, this is some generalization of some of the quantum Hall effect physics to 4+1 dimensions with 3+1 dimensional boundary instead of 2+1 with 1+1 dimensional boundary. So there are 3 recent papers where you can get some details. So my talk will be between paper 1 and paper 3 somehow. So first is warm-up. This is a really simple example for just to show you how anomalies exhibit themselves in classical physics. So the whole talk will be classical. There will be no quantum mechanics, although I will keep talking about quantum anomalies. So let me consider one-dimensional action with U1 global symmetry, which is this free boson, and the symmetry is phi goes to phi plus constant. And this model has 2 conserved currents. So one is the current which is conserved due to the Noether theorem, and there is another one which is so-called emergent current, which is conserved trivially, just because the partial derivatives commute. So we can try to introduce background gauge fields coupled to both conserved currents independently. So let me start with the vector current. So to add the gauge background field for U1 global symmetry, we just shift d phi by A. And you can see that the global symmetry becomes local. And this model has 2 currents. One is the J defined by d phi minus A, and it is conserved. But the previous current is again conserved, because it's just commutation of partial derivatives, but now it is not gauge invariant with respect to the gauge symmetry. So it should be fixed if you want it to be observable. How to fix it? Very easy. Let's redefine current. Let's call this current. But then it will stop being conserved. And if you know about chiral anomaly in 1 dimensions, you easily recognize that these are formulas which will appear in Dirac equations. It's classical physics, but we show that if we gauge one of the global symmetries, the other conserved current stops being conserved. So that's what the slide is about. So, and of course, you can also recognize that these equations are very similar to the one for one-dimensional Dirac fermion in quantum field theory, where the vector current is played by this expectation value, and the axial current is the axial current in Dirac fermions. Okay, so what about the other gauge field symmetry? So let's try to add the other current multiplied by the gauge field potential, which is different gauge potential. There is a tilde here. And this model has 2 currents, J and J axial, and which are defined by these formulas. The first one is conserved, but not axial gauge invariant. The second is gauge invariant, but not conserved. Or you can redefine the currents a little bit, and they both then gauge invariant, but they both not conserved. So you can shuffle these currents, And one way to actually, known way to actually make theory is gauge invariant in all possible ways is to couple it to three-dimensional bulk, so that this is a boundary theory, and then this additional term will make sure that everything is fully gauge invariant and conserved. But sorry, conserved, but two-dimensional part of the currents is not conserved. Okay, so that was the story in 1+1. We saw that you can see the anomalies, the conflict between some two conserved symmetries when you try to gauge them already at the classical level. So you don't really have to say that it comes from the determinant, from the Jacobian of the measure in quantum path integral. We're already working at the level of effective field theory, so it's already taken into account. So what we're actually dealing with is usually called mixed U1 cross U1 anomaly, vector and axial, and are gauging this symmetry, introducing dynamical gauge fields have a problem in consistency. But if you just think of these gauge fields as a background gauge fields, then there is no really problem with the theory, but the charges do not conserve, and that's usually called mixed 't Hooft anomaly. And this anomaly can be interpreted as a system coupled to the charge reservoir, which can be either 5-dimensional topological insulator, now I'm talking about 3+1 theory, or you can say that there may be some 4-dimensional spectator fermions with large gap, which affect charge conservation of my original system, but do not affect dynamics. So for any system with global symmetry, one can ask whether there is an anomaly, and we're going to do this for Euler fluid. So before, let me introduce what is known as barotropic fluid and show that there is axial anomaly. So barotropic fluid dynamics is the dynamics for the fluid where pressure is a function of density only. So pressure generally can depend on temperature or other thermodynamic quantities, but now we consider the case when pressure is function of only density. And the equations of motion are the equations from the first pages of any textbook on fluid dynamics, namely continuity equation, conservation of mass or charge if fluid is charged. And the second is Euler equation, which is basically F equals ma, where force is given by the gradient of the pressure. Okay. And in this theory, there are two conserved charges. There is a conservation of charge or mass, where it is defined just the integral of a three-dimensional space of the density. But also less known is that there is additional conservation law, which is a fluid helicity. So if you consider velocity multiplied by the curl of velocity, which is known as vorticity, and integrated over three-dimensional space, then this quantity is again conserved by these equations. So there is some emergent conservation law. And the question is any mixed anomaly between the corresponding symmetries for these conservation laws? And to answer the first part, we'll just introduce the gauge field. I'm following the same logic as it is one-dimensional example. So I'm saying that what does it mean to introduce the gauge field coupled to the conservation of charge or mass? Well, it's just in this particular case, it just means that I introduce Lorentz force in the right-hand side of my Euler equation. So this is electric field and this is magnetic field, which I treat as being external fields. And the question is, for these equations, is axial charge conserved or not? Okay? So it turns out that the fluid helicity density is not conserved. You cannot write a continuity equation for it in the presence of external gauge fields. And what we showed in that paper, and we tried to find it in literature, if you can help me, I was not able to find this as known result. But we showed that there is a modified fluid helicity, so not V omega is not conserved, but V times omega plus twice magnetic field is almost conserved in a sense that it's not conservation determined by the right-hand side, which is the electric field multiplied by magnetic field, scalar product. So this is, again, already looks like an axial anomaly. Yes?
I have a question. If you think of looking at the fluid in a moving system, could you interpret the electric field as the time derivative of the velocity field that describes the motion of the background, and the B as the curl of that velocity field?
That's definitely a good way to think about it. For example, this 2b, if you go to rotating reference frames, this 2b is a consequence of Larmor theorem, so it comes together with vorticity, because vorticity is twice the local angular velocity of rotation. So you can probably interpret these things this way. I'm not sure exactly how to answer this question. So for me, it's just external force, and this is because of external force. There is really no surprise that this quantity is not conserved. After all, I apply external force. Why should it be? The most surprising part is there is some modified quantity which is conserved up to E dot B. And one way, so which we can write in four-dimensional notations similarly to Dirac. So this is how it actually happens technically. So you can actually, this is like exercise for students studying differential calculus, that you can just take these equations and take a derivative, time derivative of v times omega, and use those equations many times, and you can combine it into this formula. And you see it's bad, because I put a lot of things under the divergence, so that you can interpret this as a current. But there is part here which depends actually on velocity, on vorticity, so it's really not even only background dependent, it's really non-conserving. But if you write this, which is called mixed helicity, which is velocity times magnetic field, you can also derive this equation, and it's again not conserved. But having the combination with the factor of 2u cancels this bad part, and you get only divergence into E dot B. This is how technically it happens.
What is mu?
Mu is a chemical potential, which is a function of density and related to, I use pressure as a function of density. Out of that, you can make chemical potential. Some part of these equations were known, but in the context of the plasma with infinite conductivity. If you have plasma with infinite conductivity, then E plus V cross B is 0. You can remove this, and E dot B is also 0 in that case. So you have independently conserving fluid helicity and magnetic mixed helicity, but independently. But we show that this combination is almost conserved, no matter what the conductance of the plasma is. And also, another comment, important one, is that this is not magnetohydrodynamics. I'm thinking of E and B as just external time and space dependent fields, but I do not want to think about their own dynamics or that they actually themselves are induced by the same fluid. No, I'm not talking about that. Okay? So this was a very technical way. It's not really clear why this happens and why this is a good quantity, this fluid helicity. So, and to see how actually it works in a little bit deeper way, we'll talk about variational principle for variable fluid. And also it will help us to turn on, remember we have to turn on another axial gauge field coupled to the helicity, which is more complicated to do it by just adding some force in the equations. Okay, a couple of comments before we start with variational principle. Variational principle for dynamics of perfect fluid has a long history, is quite non-trivial. You cannot just write variational principle in terms of density and velocity directly, and it has many versions. And the one we're going to use here is the one which is close to the approach by Carter and Arnold School, and involves the use of so-called restricted variations or admissible variations. Alternative version, which many people probably know, is using Clebsch parameterization of the fluid. But we are going to use this one as the most geometric and compact one. And amazing thing about this approach is that it's suitable for both relativistic and non-relativistic hydrodynamics. Many results I'm going to talk about that are independent of what the space-time symmetry of the fluid is. So it's quite elegant in this sense. Okay, the claim is the following, that the action of a barotropic fluid is just this. Okay, here we have an integral of a four-dimensional space-time of some function p, which depends on four components of some field, which is a one-form field pi mu, where mu takes values 0, 1, 2, 3. Okay, so there is some function here, which will turn out to be pressure of the fluid. So, the main part is that what we do with this action, and what we do is we say that we allow to do variations of the field pi, which are the following. We can use diffeomorphisms, where pi is transformed like this. So I'm allowed to vary this action with respect to these variations. Where epsilon is some arbitrary infinitesimal vector field. And you can recognize that this is the standard Lie derivative of 1,4. And the diffeomorphisms. Another thing, but which we will not need in this talk, are gauge transformations when you shift pi by derivative of some phase lambda. But we will not need this because it will come out for free. Okay, so using that variational principle, I will show you a few details, but using this variational principle, you can actually derive these equations. So you will derive that the divergence of the energy momentum tensor, which is explicitly given by this combination, and J is the partial derivative of P with respect to pi. So this is the energy momentum tensor which is conserved, and that's consequence of equations of motion for that variational principle which I just described. And also the current, which is given again by this, is also conserved. So, and from these equations we recognize this as energy momentum tensor, and J as a charge or number current, pi mu will be recognized as specific momentum per particle, canonic momentum per particle, and P is a pressure function, as you can see from the energy momentum tensor, this is diagonal part. Okay. So what I'm doing is I'm doing this exercise of deriving equations, and I combine them, and then I identify fields looking at the equations and trying to match fluid dynamic equations. Okay. So now, how to get actual standard Euler equations from all of this? It turns out that the recipe is the following. Take pressure as a function of chemical potential, not as a function of density, which you can easily recalculate, of course. And then, so that the derivative of pressure is density multiplied by differential of chemical potential. And then we just say that if you substitute instead of mu, this combination pi 0 and pi I squared divided by 2, and then just use equations which I wrote before, then you will get standard Euler fluid dynamics from the textbooks, which is Galilean invariant. So this way you will get Galilean fluid and non-relativistic. Okay, and then you also recognize all other quantities. If you, however, say that take this pressure, which is a function of mu, and substitute mu as some relativistic invariant made out of pi mu, then just repeating the same equations, you will get equations written for canonical momentum, current, which is given by number density multiplied by flow velocity, etc., etc. So we'll get equations for relativistic fluid dynamics. So what we get is a universal way of thinking about fluid dynamics independently on the space-time symmetry. So it's kind of very convenient.
Sasha?
Yes.
In the relativistic case, I seem to recall you have a gauge symmetry under local Lorentz transformations. Is there a way to see this here?
So, I mean, this is the Lorentz invariant, right?
Yes, sure.
So this is where I specify my space-time symmetry. I'm saying that P is mu is a scalar, chemical potential, and I want it to be actual scalar with respect to Lorentz transformations.
Yeah, sure. This I get. And you would say that pi mu is Lorentz invariant anyway. Sure. Okay. And because everything depends only on mu, the theory is gauge invariant by construction. Okay.
Yeah. So in terms of the gauge invariance with respect to charge transformations, I'll go next, because so far it's no gauge fields, no external gauge fields.
Here I meant the gauge symmetry under Lorentz, which is...
Lorentz. For that you need to introduce metric and things like that. You can do that easily, and you just put G mu there, and it will be then satisfying it. So you can introduce metric in this formulation as well very easily. Okay. So again, so what we're now a little bit of detail. So let's vary the action with respect to those admissible variations, and this is just Lie derivative of pi. So what we have is this. So we take variational derivative of the action with respect to pi, and then add delta pi, which is here, and we want it to be 0 for any epsilon. So I'm just giving you really technical details. So let's introduce the whatever variational derivative of s with respect to pi, let's call it particle current. Let's just call it this. Then the equation which you obtain from here is just this. I mean, you can easily see the first term is basically this one, and here you have to differentiate by parts and combine terms, and you can see something like that. Okay? So this is the equation of motion. So I cannot derive anything more than that with my principles. So let's now massage it a little bit. So we multiply this equation by J mu, and using this antisymmetry of this, you immediately get conservation of the current from here. That's why I said that you don't need even gauge transformations here. It's for free. So you only diffeos will lead to conservation of current. And because you know that this is 0, you throw this away and you get this nice equation. Which of course tells you that the differential form d pi evaluated on J is 0. So that's very geometric. Okay? And this is what I just said. In form notation, this is just this. So if you take d pi and evaluate on the current, it will get 0. From here, it immediately follows that d pi is 0. Okay? So this is really one-line computation. Because this, it means that d pi is not the maximal rank form, and d pi is not the maximal rank form, but it's four-form in four-dimensional space-time, so it means that it's 0. So this is 0, but this can be written as a conservation law, and this is actually helicity conservation law. So something remarkable happened here, because we started from orbital reaction. Notice that I didn't even use the fact that action is equal to the integral of pressure as a function of pi. I just said S is a function of pi, and I use functional derivative. So let me try to go back. So my starting point was arbitrary action as a function of pi, right? So I never used any particular shape. It can be with any number of derivatives, anything you want. The only condition that it depends only on pi, that there is no other fields. And then from that, we derived conservation of helicity. Yes?
I presume this would not be true if you were not restricting yourself to admissible variations. If you had arbitrary variations, that would not hold.
If you have arbitrary variation with respect to pi, you will just get J equals 0 equation, and that's too restrictive in terms of the motion of the fluid. Therefore, we weakened this, so we said that let's do only admissible variations. Yeah.
Is there a sense, you said this comes from Arnold, right? This admissible.
Yeah. That's the idea is that you consider this diffeos as admissible variations. That's.
Is there a sense in which you can think of this as a geodesic in a group of diffeomorphism or something like that?
Right. Yeah.
It's true.
It's related, but I would not comment. You see, the difference here with Arnold's is that we are doing here the diffeos of space-time.
Exactly.
Okay. So this is like a covariant way of doing this Arnold formulation. What they usually did is that they considered the flow in 3 dimensions, and then they used diffeos to optimize energy and things like that. So this is the space-time formalism. But it's of course related, but not sure about geodesics. So what we found is that this is conserved. In external field, what you do is you just replace S of pi as S of pi minus A, where A is arbitrary external field. But still, the only dynamical field is pi, therefore everything I talk about is still correct, so this is still 0. And so helicity is still conserved, but now it's not gauge invariant. And you have to remember now a one-dimensional example. So this is like kinematically conserved. That's the consequence of kinematics. But now it's not gauge invariant, so it should not be considered as a physically observable current. So let's try to make it physically observable. The good combination is this one. Why is it good one? Because if you now take the divergence of this, then you will see that it's okay, I probably have it here. So the easiest way to do it is this way. This is pi minus a d pi plus a. If you take additional d, you get d pi minus dA dA. d pi is 0 according to this, so you get minus dA dA. And you immediately derive that this modified current satisfies this equation. Okay, remember those long formulas in non-relativistic case, which I showed you before, showing that this is true. Now it's done, and it's done in relativistic, non-relativistic, for any type of action. So it's purely kinematic formula. And that should remind you axial Chiral anomaly. And in Dirac. Yes.
Sorry, maybe I get a bit confused. But how is it? It's cancelled the mixed term, d pi dA?
Yeah, it's d pi minus dA times d pi plus dA. Yeah. So it's a squared minus b squared type of thing. These are two forms, they commute.
Ah, okay.
Yeah. So, so that's the axial anomaly in this language. And now we have to try to turn on another extra gauge field, which is coupled to this current, and see what happens with the vector current. So how they actually mutually affect each other. Any questions? So, okay, still good with time. So, so this is the action of the charged barotropic fluid, and we think about adding some higher gradients of fields. So let's just add this term. So I probably change notations. So this is now not a tilde, but a axial. This is a new gauge field, not a. And it's multiplied by z current, which we introduced before, right? I wrote it in differential form language to stress that this term does not depend on metric in any way. Because it does not depend on metric, it is not supposed to change energy momentum tensor. So I expect the same energy momentum tensor, and only currents will be modified. Okay. So the extra term is topological, so it doesn't contribute to energy momentum tensor. It's basically as axial gauge field multiplied by axial current, which we introduced. And it's gauge invariant with respect to a field, completely gauge invariant. It's not quite gauge invariant with respect to this axial field. But its gauge non-invariance is only due to the background field. Okay, so let's consider this action. I have to say that some time ago we introduced this action where instead of this axial gauge field we use the same A field, and that was the idea to describe wild fermions with only one component of the gauge field. So then the details in this work. So variation principle gives again this equation, because nothing changed, it still depends only on one dynamical field pi, and we showed that it's very generally true. And explicitly this particle current now, you just have to take that action and vary with respect to pi, is given by the previous current, which is something like n times u in the relativistic case. But then there is a correction due to the derivatives. And immediate consequence of this is still that this equation is still the same, because we derived it without taking into account any particular form of the action, so it's still correct. The question is what happens with actual currents and with energy momentum tensor. Okay, it turns out that you can derive the following equations. You have to take the previous energy momentum tensor, except that now it's gauge invariant, and the divergence of this energy momentum tensor is given by two terms, two Lorentz forces. One acting on vector current and another is acting on this axial current, which we introduced. And you can derive explicit formula for this current. This is called, in the language of anomalies, these are called covariant currents. So this is covariant electric current. So and it's given by this formula. So it's original current but corrected by this expression. And you can show that the divergence of this current is equal to by this, which is again should remind you that this is like f times f axial term, which should remind you the Dirac fermions again. But okay. So this is summary. So we have these equations of motion, and notice that I wrote here 6 equations of motion. There are 4 equations here because nu takes values 0, 1, 2, 3. There is one conservation of this current, non-conservation of this current, and there is one non-conservation. There are 6 equations here, and I have only 4 fields: pi 0, pi 1, pi 2, pi 3. So these are still compatible equations. They derive from the same variational principle. So you essentially can start with any 4 of them. You can start with energy momentum tensor and derive these guys or do some other combinations. But they are not independent equations. They are compatible. And these equations exhibit covariant mixed anomaly between charge and helicity conservations, as I promised. Okay, some small comments that we have several currents here or fields. The one is this specific kinematic momentum. The J is electric current. This is particle current. If you have Galilean fluid mechanics, they basically without external fields, these currents are proportional to fluid velocity. But in a relativistic system, momentum becomes not proportional to velocity, and in the presence of background fields or anomalies, these all three quantities become totally separate fields. Somewhat related, but okay. And as one application, what we can do is we can try to find equation for stationary flows for these hydrodynamics in the presence of external axial and vector fields. So what we are going to do is we are going to assume that all our external fields are time independent. For simplicity, just to make equations smaller, easier to read, we put axial external gauge field to be 0. So only electric or chemical potentials we will leave. And then equilibrium conditions is that the vector part of this particle current equals 0 and pi 0 equals 0. And they give this equation which specifies equilibrium configurations. And notice that if there is no external magnetic field, no external axial electric field, then this becomes velocity proportional to omega. These are known as Beltrami flows. So basically saying that velocity is an eigenfunction of the curl operator. So omega is the curl of velocity and it's proportional to velocity. So it's, this is known condition known as Beltrami condition. Here it's generalized because there are external fields and also everything here is in principal space dependent, but not time dependent because we are looking for stationary flows. So using this condition and using the expressions for current which are general, which I showed before, you can actually find that in that state, which satisfies this, the vector current is given by this formula, and the axial current is given by this formula. So notice that there are two kinds of terms here. Some term is just like this one is proportional to magnetic field, and this one is a total curl. They usually say that this is transport current, and this current is a micro motion, like circular motion or diamagnetic current or something like that. So these formulas we can generally derive. To connect to the previous literature, suppose that we have now electric fields to be 0 and chemical potentials to be constant. Then you get these expressions. So now I don't have electric fields, but I don't have gradients of chemical potentials. They're constant, so I simplify these equations to get this. And what I obtain is that there is a current proportional to magnetic field, and that's already in the very early paper by Fröhlich, Alexeyev, and Shianov, and this is a consequence of the anomaly, what they did for Dirac fermions. So there is this part. In literature, it's very often called Chiral magnetic effect, the part in constitutive relations for current which is proportional to external magnetic field. And chiral chemical potential, this imbalance between, if I'm talking in terms of Dirac fermions, then this is just imbalance of chemical potentials between right and left well fermions. And there is another part, which is that actually there is a component of the current proportional to vorticity, and that's known as chiral vortical effect. And these were all parts of the Son-Surovka equations, for example, and many other people. And the axial current also can be written as this one, and this is less used, but there is also a name for chiral separation effect when you apply magnetic field and you have axial current, and chiral vortical separation effect. So all these four terms were already seen in literature, but what we have is the full fluid dynamic equations. So these are only relations in a stationary states. Okay. And I am really early. Okay, so talking too fast. So let me go slowly through conclusions. Background gauge and axial fields. Gauge fields were introduced for perfect barotropic fluid. There is a mixed anomaly between the charge and helicity conservations. So if you try to gauge one of the symmetries, introduce gauge fields for one of the conserved quantity, you will violate the other one. We formulated the variational approach, and of course you can, having action, you can write Hamiltonian and write commutation relations for those velocity and density fields. And we considered also stationary solutions, which are given by generalized Beltrami flows, and there are some interesting relations between between the various parts of the currents, the constitutive relations. Just a couple of open questions. So it would be really nice to apply this and to realize those external gauge fields in real systems. It's not difficult to realize electric and magnetic fields, the first part. For example, in plasma, they use it all the time. The realization of axial gauge field is a little bit more complicated, but I would suggest two ways to think about it. One is that you actually can realize those in a model system. For example, if you take what is known as well semimetals, and if you assume that there is some regime when those well electrons behave as fluid, which is non-trivial because you always have impurity scattering and you need to get into hydrodynamic regime. But if you have this, then when you deform the lattice, the distance between wild points is changing by stresses, and this distance is like a axial vector potential here. So playing with the dynamical time-dependent and space-dependent stresses and strains, you can in principle modulate things like that. That's one way of thinking about it. Another way is the following. So we know in statistical mechanics, statistical physics, that we often introduce the external fields coupled to the order parameters, even if those external fields do not exist in nature. For example, we talk about staggered magnetization when we study antiferromagnetism or superconducting fields. So it's useful from the formal point of view to introduce those conjugated fields in thermodynamic sense. So in this sense, these axial gauge fields which we introduce are conjugated to helicity density and to vorticity, to these quantities. So in principle, I can study some complicated configurations with distributions of helicity just by tuning on those fields and finding stationary solutions to these fields, and then maybe releasing those fields and looking at the dynamics. So there is a more formal way, but it would be nice also to realize it in nature directly. So there is another part where we can actually show. Remember that in this approach for barotropic fluids, the charge conservation, the actual vector charge conservation, came also from diffeomorphism, right? I use only admissible variations, which are diffeomorphism, and as a side product, I get that d mu j mu equals 0. So the conservation of vector charge is also part of this diffeomorphism group, and the helicity conservation is another part of the same diffeomorphism group. And they are embedded in the one big diffeomorphism group, and they kind of not independent from each other, and that's why they conflict if I want to make them local. It would be nice, well, I have explicit formulas of how to think about it, but it would be nice to really understand it deeper related to the structure of diffeomorphism transformations of diff group. And one important big thing, which we have some progress, and some progress is known in literature also, is that what happens if pi is not the only dynamical field. For example, you have entropy, so meaning that you want to consider not only barotropic but also baroclinic flows where pressure is importantly function not only density but also temperature. So in this case, so it is not so simple, as well as hydrodynamics with many species of particles which are interacting. But some variational approaches for this also exist. They are less transparent than the one I suggested here. It would be nice to generalize this story to the more complicated systems as well. And probably I stop here.
Thanks a lot. Questions or comments? Yeah.
So the mu A, this chiral chemical potential, can sometimes be interpreted as the time derivative of an axion.
Right.
And you can look at axion electrodynamics and so on. Would there be an interpretation in fluid dynamics for the axion?
I'd love to discuss that. I do not know. For us, it's just external. I do external gauge fields, and mu A is a property of fluid dynamics. I know the work of you with Pedrini and with other people where we use axial. And we also see some interesting features here that very often it's when you introduce general backgrounds, then it seems like that there is some internal degrees of freedom which becomes alive, which I cannot say precise things about this, but it seems that roughly like this. So if you think now about resolution of this pi in terms of Clebsch variables and write that pi is d theta plus alpha d beta plus whatever pairs, then that theta field it wants to be like independent fields. So according to this variational principle, it's not allowed to write theta, alpha, beta separately from pi. It's just, they should come in this combination. But it seems that for many purposes it is useful to think of theta as an additional degree of freedom. And it is probably related to the fact that if you want to really describe the underlying spin of those fermions, and you really need that. But I mean, I don't want to hand wave too much. It would be nice to think about axial field in this context.
More questions?
Yeah, very basic, maybe naive question. So in functional quantum Hall liquid, it's incompressible, so the pressure is zero, but its density is also constant. So is that a special case of the barotropic fluid?
No. Like technically, for definition of barotropic fluid, you talk about compressible fluids, and continuity equation for velocity and density is part of the system of equations. If you want incompressible fluid, then you replace continuity equation by divergence of velocity equals zero, and then pressure is not a function of state anymore. It's determined by velocity. So, and the quantum Hall is in this. You can extend it a little bit, and you can write. And I did this some time ago. You can write hydrodynamic equations in 2+1 with velocity and density, and assuming that it's like a compressible, but then impose constraint on it that the density minus background density equals the curl of velocity, equals vorticity. If you impose these constraints, the liquid effectively becomes incompressible. And, but it's incompressible effectively at large distances. At short distances, you can squeeze the fluid and it will rotate faster, so you can still have this response. I have to say that if you think about analogies, there are many analogies with any dimensions here, but the most analogous thing here is to 1+1, because as we know in anomalies, the analogies go through 2 in dimensions. But this is still analogous to quantum Hall. But if you think not about bulk dynamics of the whole fluid, but about the edge state, yes, and then it is a very precise analog of this. And you studied also for dimensional analysis of quantum Hall effect, which is this is just fluid realization of this in terms of the fluid dynamics.
Thank you.
So you said that in your variational principle, you would have to restrict to admissible variations.
Yes.
What about the following proposal of why this is so? So if you do point mechanics, you do variations of positions, and if you pass the continuum limit, and this is naturally done in the Lagrangian picture, then this is a diffeomorphism. Is that the reason why? Absolutely,
absolutely. I mean, I skipped all this, but this is really well developed topic. So technically, how do I do admissible variations of this pi field? I can say that pi is equal to d theta plus alpha d beta, where alpha beta are some scalars, and then I do independent variations of alpha beta theta, and it will do these Clebsch parameters. Those alpha beta have interpretation of Lagrangian coordinates of the fluid. The whole reason for this weird behavior, like you see, it's even more weird in a sense in Hamiltonian formulation. You can write easily Hamiltonian for Euler fluid, but then you notice that this v dot omega integral over space commutes with everything. So it basically has zero Poisson bracket with rho and v separately. And of course it's conserved for any Hamiltonian you can write, because it commutes with fundamental fields. The question, why is this degeneracy? The answer is because the Euler fluid dynamics is not a complete story. The complete description of the fluid is Lagrangian dynamics. And when you reduce and forgetting about which particle comes from what, and you look on the density and velocity at this point, you do some kind of gauge Cosat, and that's why it's incomplete dynamics, but having this hidden Casimir and so on. So you're absolutely right. That's exactly the reason for restricting those variations. Yeah. Because they correspond to the relabeling of particle in Lagrangian dynamics.
All right. Any more questions or comments? If not, Sasha, thanks again.